Hello everyone. Today we will discuss normal thrust and radial shear in two-hinged arches, then effect of temperature on horizontal thrust in arches, and effect of support yielding, which is also called as sliding of supports in arches. So there can be the cases when supports are failed and they undergo some displacement. So here also we will see the effect on horizontal thrust, then effect of rib shortening. In this case actually length of arch decreases due to compression. So its effect on H that will be studied. So now let's start. First is normal thrust and radial shear. So consider an arch like this. It has got some loading on it. There can be UDL, etc. Now in this case H is horizontal reaction, which is also called as horizontal thrust, and then we have vertical reactions at the 2 points A and B. Now consider a point somewhere on the support on the arch, let us say point D, and coordinates of D are x and y with respect to A. So we are taking A as origin. So this distance is x and this height is y. Now bending moment at D in case of arch is given by beam bending moment minus h into y. So we know this formula, where M beam is bending moment in an equivalent beam. That means the beam of the same span L, exactly same span, same loading, and it's at the same point D. So M beam is the bending moment at D in case of the beam. Now shear and thrust in arch at D. So if I consider free body diagram of AD, so that will be like this. Your point A, which is under equilibrium due to H and VA, and at point D we have horizontal thrust, say HD, and then we will have vertical shear VD, and if I draw a tangent at D to the curvature of arch, this is tangent at D, say angle of this tangent with horizontal is theta, and there can be some external load like W1 here. So this is a free body diagram. So this particular free body diagram is under equilibrium due to the following forces: H, VA, W1, which is external load, VD and HD. VD is vertical shear at D and HD is horizontal thrust at D. Now I want to break VD and HD along tangent and perpendicular to the tangent. So this is normal to TD. TD is tangent. So if I consider point D separately here, we have got H as horizontal thrust, VD is vertical shear. At this particular point in the arch, we have got components of VD and HD along tangent and perpendicular to the tangent, that is along normal to the curvature. So this component of these VD and HD, which is along the tangent, that is called as normal thrust, and we denote it by ND, whereas this component which is along the normal is called as radial shear, SD. So ND and SD are perpendicular to each other. Now consider this portion only. At point D, we have ND is equal to HD cos theta plus VD sin theta. It is so because HD has got two components, one along tangent and other perpendicular to the tangent. So we can draw it like this. So this component, which is along tangent, will be HD cos theta. And we have VD, which is vertical. VD also has two components along tangent and perpendicular to it. So this angle is theta. So this component would be VD sin theta. So considering these two components, this one and this one, both of them are parallel and in the same direction. So we have VD sin theta and HD cos theta, and both of them are making ND, that is normal thrust at D. Therefore we add them and write here. So this becomes normal thrust at D, which acts along the tangent at D. Now let us find out radial shear at D. Normal component of HD will be HD sin theta, and it is acting in this direction. And normal component of VD is this, which is VD cos theta, and it is acting like this, VD cos theta. So these two are in fact making up radial shear at D. So we can write ST equal to VD cos theta minus HD sin theta, because these two are opposite. So we take the difference of the two and get this relationship. So using these two equations 1 and 2, we can easily get normal thrust and radial shear at any point on arch. Now one important thing that should be noted here is that ND and SD, they are simply the sum of components of horizontal thrust and vertical shear at any point. Radial shear is simply a sum of components of horizontal thrust D and vertical shear at D along normal to the arch. Whereas ND, which is normal thrust, it is also the sum of components of HD and VD along tangent to the arch. And the directions of these are like this. At any point, we have horizontal thrust HD, which should be essentially equal to horizontal thrust in the arch, because there is no horizontal force in between A and D. So if this is H, HD will also be H. If there are some vertical loads, they will not affect the value of HD. It will go directly as H. And vertical shear is VD downward. ND is taken as like this, and SD is taken as like this. So that's all for normal thrust and radial shear. Okay, we will now consider effect of temperature on arch. Basically, when arch has its horizontal thrust as H, due to rise in temperature, it will try to expand. But we have got hinges here, there is no roller, so it will not be able to expand, so it will develop compression in it. So compression will develop, and that will give rise to H. H will increase. Now let us derive the formula for H when temperature is affecting the arch. So consider this arch of span L, and let us say there is no loading on it. Bending moment at any point, say P, we take any point P somewhere, at a distance of x and height y from A, where point A is taken as origin. So bending moment at P is given by this formula, VA into, where VA is reaction at A, at P we have reaction VB, so it will be, MP will be VA into x minus H into y. So what is VA? It is simply beam bending moment at P. So let us say delta T is increment in temperature and alpha is coefficient of thermal expansion of the material of arch. So what is the strain in arch? That will be equal to alpha into delta T. If one of the supports, let us say support B, is made roller, then what will be the change in span of arch? That will be delta L is equal to strain into original span, that is L. So strain is alpha into delta T into L. So this is the change in length, and that is also equal to horizontal displacement at B. So consider here, if B is made roller, then what will happen when temperature is increased? It is going to expand. So if B is changed to roller, due to increase in temperature, this support is going to travel up to B dash. So this displacement of B is delta L, or we call it as delta B. But when we convert it to roller, H will become 0 simply because horizontal motion is allowed, so horizontal thrust will become 0. But suppose we apply a force here, which is H, so that this arch comes back to its original position. We push at B with a force H, so that arch comes back to its original state. So we are pushing it in this direction, B dash to B, by the same amount, that is delta L. So now we have delta L being reversed by a force H applied at B dash. So we have H towards left, delta L also towards left. So according to Castigliono's second theorem again, if we apply this formula, del U by del H equal to, it must be delta L, because delta is displacement along H. So as per Castigliono's second theorem, we can write this. And we know U is equal to integration of m square ds upon 2ei, that is the strain energy due to bending moment at any point P, and we integrate over the length of the arch, span of the arch. So in this particular case, we have MP is equal to Vx minus h into y. So it is obtained earlier. So right now here MP square ds upon 2a. So let us differentiate this u with respect to h. So we get del u by del h is equal to integration mp into del mp by del h into ds upon 2ei. So we have 2 here also. So 2 will get cancelled. So we will get it as integration mp del mp by del h into ds upon ei. Now put this value of MP here, keeping Vax as MB. It is simply bending moment in the equivalent beam of the same span. You know, del U by del H is delta L. So it becomes integration MP is MB minus H into Y into del MP by del H. Now differentiate MP with respect to H. So that will be obtained as MP is equal to 0 minus H into Y. So it will be 1 into Y. So del MP by del H will be 0 minus Y. So it is minus Y. So we have minus Y into ds upon EI. But here delta L is alpha delta T L. So we can get it as MB into minus Y. So it becomes minus MB into Y upon EI into ds plus integration H into Y square ds upon EI. So H is a constant, it can be taken outside integration. So we can get H here, and H would be, carry this term to the left hand side, then H can be obtained as integration MB into Y ds upon EI plus alpha delta TL divided by integration Y square ds upon EI. So this is the formula that we use for calculating H when temperature change is there. So if you compare it with the original formula of H that had only this portion, this is H when delta T 0 means there is no temperature change. So temperature is constant. So we use this formula. So this extra term is there in numerator, alpha delta TL. This is the extra term in numerator if delta T is not 0. So if there is still change in temperature. So here it can be noticed that if delta T is positive, that means that H will increase. So if there is a rise in temperature, horizontal thrust will increase, and if delta T is negative, there is a drop in temperature, H will decrease, because this term will become negative and it is going to decrease H. So if we are given alpha delta T, then we can easily get new horizontal thrust, which will of course be less than H if delta T is positive, and it will be more than H if delta T is negative, means there is a drop in temperature. So that's all for temperature. Thank you. Now let's take the case 3, effect of support yielding on arch. So basically we will study their effect on H, that is horizontal thrust. So what happens when there is an arch due to some foundation failure of abutment or due to cracks in abutment or due to some man-made events like blasts, etc. One or both the supports may get damaged and they may slide. So due to loading on the arch, it may acquire a new shape like this. There may be some sliding of one or both the supports by some amount, and that is going to expand the span of arch slightly, and it is going to change the horizontal thrust. Generally, if there is expansion like this, sliding outside, then H will decrease by some amount. Now we will derive a formula to get the new H due to sliding of the support or support yielding due to this yield, that is, say delta. Suppose this yielding is delta. Let us consider this arch AB, and It is very similar to what we have done for temperature change. In that case, delta, which was delta L, it was given by alpha delta T into L. It was for temperature change. And then we applied some horizontal force at B to bring back support B to its original position. But here reverse is happening, because in earlier case, in case of temperature change, delta L or delta, that is displacement of the support, was parallel to H and along H. So direction of delta as well as H was same direction. The same direction of H as well as delta L. But here what is happening? Delta is outward, that is support yielding is outward, and H is acting opposite, that is horizontal thrust is already there and it is opposite to delta. So because of these opposite directions, there will be change in formula for delta. So we know, according to Castigliano's second theorem, del U by del H must be equal to displacement along H, which is minus delta in this case. So here negative sign indicates opposite directions of delta and H to each other. So that's why we have negative sign here. So rest of the derivation will remain same. So delta is generally given in terms of distance. So there can be, say, 10 mm support yielding. So we will take this as minus 10 mm. If we are taking span in meters, then we have to convert this into meters. So this will be 0.01 meter. Now, following the same procedure as we have done for temperature, we will get a similar formula except this, that we will have negative sign before delta. H will be obtained here as integration m beam into y ds upon ei minus delta divided by integration y square ds upon ei. So this is the change here. We have a negative sign. So delta is generally given. So we can easily get H. So if delta is outward, which is generally the case, supports are going away from each other due to yielding, then H will decrease, because there will be a release, there will be some motion allowed in horizontal direction, so H is going to drop. But if delta is inward, that means supports are getting closer, which is rare case, although in that case H will increase. So here it can be easily seen that decrease in horizontal thrust will of course be delta upon integration y square ds upon ei, which is simply this much portion. So it is decrease in H, of course, because H later minus H original. H is original means when delta was 0. H later is when delta is given. So there is some support yielding. So of course we are going to get this relationship, this expression for change in thrust. That's all for this case. Thank you. Now let's take the case number 4, effect of rib shortening on horizontal thrust H. So what is rib shortening actually? Due to normal thrust, which is essentially compression, It says compression type force. It tends to decrease length of arch. So this portion of the arch is called as rib, this entire formation of the arch. So due to compression coming from normal thrust at any point, so there is a compression developed, compressive stress, and that is going to affect the horizontal thrust also. So in this case, we need to consider normal thrust, that is N. Consider an arch. It can be parabolic or semicircular or circular arch. AB of span L, V and VB are the reactions. H is horizontal thrust, which is same at A and B both, and there can be some loading on it. C is ground, which is the topmost point of the arch. Consider a point somewhere on the arch, that is a point X, whose coordinates are X and Y related to point A, which is treated as origin. We have x-axis, then y-axis, running like this. Now at X point, we can always draw a tangent to the arch. So this is tangent at point X. At point X, we have normal thrust, which is along tangent, which is nx. And then we have radial shear, which is sx. So we are interested in normal thrust nx because this is responsible for rib shortening. Now let us say angle of this tangent with horizontal is alpha, and we have horizontal thrust hx, then we have vertical shear Vx. So Nx can be expressed as Vx sin alpha plus Hx cos alpha. And now Hx will be H itself, horizontal thrust at A and B. Because if we consider the free body diagram between A and X, horizontal reaction at A will be transferred to X as it is, because there is no horizontal load anywhere between A and X. Only vertical loads are there. So Hx would be HA, which is H, when we apply sigma is equal to 0 equation on this part of the arch. Now, having obtained this, let us get strain energy in the arch due to bending moment. So that is simply what we have been expressing always. So that is UM, that is strain energy due to bending moment. That can be given by integration mx square ds upon ai. And then we have strain energy due to normal thrust, which is essentially like an axial force because it is acting along the axis of the arch, and that can be given by un is equal to integration of nx square ds upon 2ae. So we know p square l upon 2ae is the formula for strain energy when P is a force causing compression or tension in any bar, L is length, and A and E are the area of cross section and modulus of elasticity of a bar. Mx is nothing but M beam minus Hy. So that is known to us. Bending moment at any point in the arch is equal to bending moment in equivalent beam at the same point minus H into Y. H into Y is actually hogging moment, and M beam is sagging moment. So M beam is going to produce bending downward, but H into Y is going to produce hogging. Now total strain energy will be U is equal to U bending moment plus U normal thrust. This can be written as integration of mb minus hy into ds the whole square into ds upon 2ei plus integration nx square ds upon 2a into e. E is modulus of elasticity of the material, Young's modulus, and A is area of cross section at point x. Now, as usual, differentiate u with respect to h and equate it to 0 because there is no support yielding. After differentiating u with respect to h, we get it like this. Del u by del h will be equal to integration mb minus hy into minus y. So this we have done earlier into ds upon ei plus integration differentiation of nx square will be 2nx into del nx by del h. So it is partial differentiation. So Vx will be treated as constant and x which is h will be treated as variable. So differentiation of nx with respect to h, simple. It will be 0 plus cos alpha because this is a constant. Partial differentiation with respect to h. So second term in strain energy is obtained as V cos alpha, Vx cos alpha plus h cos alpha, which is nothing but nx, into cos alpha, which is nothing but del nx by del h into ds upon a into e. And this is equal to 0 because there is no support displacements. Minus integration my ds upon ei plus h into integration y square ds upon ei plus integration vx cos alpha sin alpha upon a into ds plus h integration cos square alpha ds upon ei, and this is equal to 0. Now from here we can get h. So h can be taken as common from these two terms, and we can get h as integration my ds upon ei minus this term integration vx sin alpha cos alpha ds upon a divided by these two terms added, integration y square ds upon ei plus integration cos square alpha into ds upon a. So this is the formula for horizontal thrust when rib shortening is happening. Now let us further simplify this. Consider this term a upon cos alpha in this expression. A upon cos alpha is a, and this is nothing but mean cross-sectional area of arcs. So here let us understand it clearly. At point x in the arch, if we cut the arch along the normal or perpendicular to the tangent at x, we get some cross-sectional area, and that cross-sectional area is cos A. This is the cross-sectional area over which nx, that is normal thrust, is acting and creating rib shortening. If I cut the same arch at x vertically, if we make a vertical cut here, then the area exposed will be different. So if we compare the two areas, A and this area which is obtained after cutting the arch vertically, there is some relationship between the two. This area on which NX is acting and this area which is obtained after cutting it vertically, on which HX, which is horizontal thrust, which is again F, is acting. So they have a relationship between themselves. We know angle of NX is same as angle of tangent, that is alpha. So same will be the angle between A and this area AX, and this angle is alpha. So here in this triangle we can easily write A will be AX cos alpha, or AX will be A upon cos alpha. So it is this mean area which is used here, and of course AX will be more than A, and value of AX will be minimum at crown, because wherever the crown is, if we make a vertical cut at the crown, suppose this is the crown in the arch, if we make a vertical cut here, so area AX will become area at crown, and that will be definitely minimum, because as we go away from the crown, vertical depth of cut is increasing and AX will increase. So generally we take it as AM, which is AX in fact, and this mean area is calculated from average of the two areas at crown and at support. So this is area at crown plus area of the arch at supports divided by 2. So that is mean area. So this is also called as springing, area at the springings, that is the supports. So wherever the support is, we can of course have a vertical cut at the support, and this area is obtained here, which will be highest. So AX is highest here. So minimum at the crown and maximum at the supports. So we take the mean of the two. Now let's go back to the expression of H. Here we can work upon this term using A by cos alpha as AM. We can say that integration of cos square alpha into ds upon AE can be reduced to integration of cos alpha into ds cos alpha upon AE. So cos square alpha has been separated into two parts. Now here A by cos alpha is 1 by AM from here, and ds cos alpha is dx, because ds is a very small length considered at x, and dx is its horizontal component. So that is dx is equal to ds cos alpha. So that can be written as dx here. So this becomes integration of dx upon am into e, and am and e, they are constant. So integration of dx will be span L upon am e. So this is the one of the terms in denominator. Secondly, effect of Vx, which is vertical shear force at x, is negligible on rib shortening. So it is obvious, because rib shortening is mainly caused by normal thrust, with major component of normal thrust comes from H, not from V. So effect of V in this expression can be neglected. So that means this term can be neglected for simplification, as well as for the reason because Vx is not affecting rib shortening much. So neglecting this effect, value of horizontal thrust becomes integration m b y ds upon ei divided by integration y square ds upon ei plus L upon am. This has been integrated already over the length, so we do not have integration of the last term. So this is the formula which is giving us horizontal thrust after rib shortening is considered, is taken into account. Now here everything is known to us, and generally if I is I naught secant theta or secant alpha in this case, means moment of inertia is having secant variation, in that case we know that ds can be written as dx secant theta, I can be written as I naught secant theta, same here, ds is dx secant theta, I is I naught secant theta, where I naught is moment of inertia at crown of the arc, that is C. So in that case secant theta will get cancelled in their respective terms, so h can be simplified to this formula, integration m being y dx upon ei naught on integration y square dx upon ei naught plus L upon a and e. So it is observed here that this particular term is extra if rib shortening is there or it is considered. The rest of the formula is just the one which we have already derived for nominal cases, for conventional cases, for no rib shortening. So it can be observed here, due to this extra term which is positive, the denominator is going to increase, therefore h will decrease. So when rib shortening is considered, horizontal thrust will decrease by some amount. Now finally, when we consider everything, means we consider temperature change delta T, when we consider support yielding, and also consider rib shortening, then h will have this formula, integration m being y dx upon ei naught plus alpha delta TL minus delta, this delta is support yielding, delta T is change in temperature, divided by integration y square dx upon ei naught plus L upon am. So when everything is there, we use this formula, because from principle of superposition we can include these two, temperature change and support yielding. And that's all. Thank you for paying attention.